So we're going to continue on with chapter 9, which is moving from the realm of brick into stone and concrete masonry units. And I find it really interesting that they separate out brick and concrete masonry units. To me, those two should be in the same vicinity, and that stone should be separate. But I guess maybe they were trying to fill up the stone chapter with a little bit more. So anyway, we're going to go through both as part of chapter 9. So as we get started, the first thing we kind of have to talk through are the basic stone types. And this is not by any means my area of expertise. There are plenty of geologists and stuff that can talk far more in depth about rock types and how they're made and whatever. So it's my goal to try to give you kind of an overview of the things that are important about it in relation to building rather than a true geology lesson on where this rock comes from and that sort of thing. But we have basically three types of rock that we'll use in buildings. First, we have igneous rock, right? This is the type of rock that's volcanic, that's deposited in a molten state, right? We have sedimentary rock, which is rock that's deposited by water and wind, right? That builds up in small, fine layers, right? And then the last type is metamorphic rock, which is igneous or sedimentary rock that's been transformed by heat and pressure, right? And so we use these in different times in buildings, and we're going to talk about where we would use those and why. So the first type is igneous rock. It's granite. It's non-porous. It's very, very strong. It's very durable, and it's the most permanent of the building stones that we might use. How many people have come in contact with granite before? Right? So I would say maybe 10 years ago it started to become really in vogue to have granite kitchen counters, right? And so that's probably where you came in contact with them. I have a bunch of samples that I will pass around. Chances are you've probably seen most of these already, but you can certainly still look at them now, right? The thing about it is there is quite a color variation, and certainly if you've ever picked kitchen granite or you've gone to a place that has granite, there are a bunch of styles, right, available. There's a bunch of colors available, and there's a bunch of grades available that are still all granite, but depending on the look that you're after, you can pay very little to very much, right, depending on the color and the look and that sort of thing. So it's not a surprise that we use this primarily for our kitchen countertops in buildings because it's non-porous, right, and it's very, very strong and durable. So non-porous means that if you spill something on it, right, it's not going to absorb whatever it is that you spill on it, which is a good thing, right? We do other things like we seal off the counters to try to make sure that nothing gets on top of them. And if you have granite counters or have ever maintained them, you realize that you do still do things to it. But it's not a surprise that this is used in that context because it's such a durable stone. Okay, that's not to say that the only place granite is used in a building is on countertops, right? It can be used a lot of other ways in a building, but that's its primary use. Okay? So the next stone type that we'll talk about is limestone. Probably the most common version of limestone that we see in buildings is travertine, but it's just a variety of limestone. I have some examples. Most of these are travertine, but you guys can take a look at these. There's those. I think I have. Those are all. So let me steal. You guys can have a couple too. So limestone is sedimentary rock. It's porous and contains a lot of groundwater when it's see quarried, right? So it has water already in it. One of the samples that I passed around shows all of the cavities that are in it. Let's see if I can find that one again. Did you guys already pass the one with all the holes in it? No? What did I do with it? This one. Perfect. Right? So, you guys can see on this one, right, there's a bunch of little cavities and holes in it, right? That can absorb water, right? Which also makes it kind of a challenging building material because it absorbs water, right? So it's something you have to pay attention to, right, in relation to limestone, okay? After what's called seasoning, right, the stone does become a little bit stronger once you remove the water, right? The other thing that happens if you're going to use travertine, say, as tiles in your bathroom or something like that, which is kind of common now, or on the floor or whatever, is a lot of times it's filled, right? So you have a certain amount of natural stone that corresponds to like that one that has all the holes in it, right? But if you look at one of the other pieces that I passed around, there's a bunch of filler material that's been squished in around those holes and then polished, right? And so that filler material helps to make it more waterproof than it would otherwise be, right? Yeah, is that the one with the holes in it or the fills? Yeah, so this one's a little bit more of a natural limestone, right? But you can see, right, like this. That's a fill. That's a fill. That's a fill. So they put an epoxy in it. In this particular case, it's a clear epoxy. Can I borrow this one for just a second? Right. On this one, it's a colored epoxy. Right. And so those little fills go in to make it a solid waterproof surface. Sorry. Right. Yeah, you could use it on a countertop. It tends to be more porous, so it accepts more. So countertop's a little iffy, but say a bathroom shower or a bathroom countertop or something like that would be more of a common use for it. They don't get as much rain, and so depending on how it's filled, right? Certainly, it has a very soft quality to it and a soft look. If you're in Italy, right, a lot of the buildings actually have limestone cladding, right? So, and Italy does get rain, more so than Los Angeles. So it can work. It just depends on the grade of the limestone, how many holes are in it, how filled it is, right, and that sort of thing. And recognizing that it can absorb some of the water, right? So we move from there into a third stone type, which is called slate, right? Chances are you've probably heard of slate before, right? It's a metamorphic rock, which means it's another type of rock that's undergone heat and pressure, right? I have a couple examples that I'll pass around of slate here, right? The important thing to look at when I pass these around, right, is that it is a very dense, heavy stone, right? But it's also, it can, if you look really carefully at the edges of it, right? And so when it passes around, you can see this a little bit better. It's made up of a lot of thin little flakes, right, that are compressed together, right, which makes it really easy to split into sheets, right? Because those little basically cleavage is what they call it, right? Can be really easily split into sheet goods, which makes it a really good building material for things like paving, right? Pool tables, yes, or roofs. Right, because we can split it into thin sheets that we can use, and the sheets are relatively durable, right? So when you pass these around, just make note of the edges of what those edges look like, right? And again, it comes in a variety of materials or a variety of colors, right? So we move from there into the world of marble, right? A couple examples of marble that I pass around. These ones I think are marbles, but they're not labeled. So I'm nervous as to passing around. It looks like a marble to me, but I'm not entirely sure. Sometimes when this stuff gets in here, you lose track of exactly what it is. So I don't want to pass that one around because I'm not sure. Right? I know this one's marble. Right? It's a recrystallized form of limestone. It's again a metamorphic rock transformed by heat and pressure. Right? It's very easily carved and polished, right? It's the primary thing that, say, Michelangelo would have used to carve a sculpture, right? It's a very, very pretty material by itself. It can be carved and polished relatively easily. Not a surprise that they're choosing to make carvings out of marble. There are 4 steps to grading it from A to D that sorts for favorable qualities in the marble, right? Marble can be relatively inexpensive to very, very expensive, depending on the grade, right, and the quality of the marble. It, again, comes in a variety of colors. The ones that I passed around, we have one white that's kind of a Carrara marble look. That's very Italian marble. The other one that I passed around is a different color. It can be green. It can be blue. There's again, a variety of options that are out there. So we have to somehow, right, get the stone from its natural state into a way that we can use it in a building. And so it's fine for me to talk about the basics of these materials and pass around these little samples, but somehow we have to get from, right, where it's naturally in the ground, right, into something like this that we could actually use in a building, right? So there's a challenge to that. So we're going to talk about quarrying and then milling stone, right, which is basically the process through which we get the natural stone into some form that we can use in a building, right? So we have something that's called field stone, right, which is basically building stone that's obtained from riverbeds, right, and rock-strewn fields, right? So the idea behind field stone is that you walk out your door and you collect the rocks that are on the ground, right? And so there's nothing particularly fancy that's done about it, right? It's just a way of collecting it. And depending on where the rocks come from, they have very different qualities and looks to them, right? And you'll see a bunch of examples as we go along, right? Rubble is actually a quarried irregular fragment, right, that have at least one good flat side, right? And so it has some quarrying process. Usually it's the leftovers of other processes, right? But it's more of a broken look. It's not something that's shaped into a perfect shape just yet, right? Then we move into dimension stone, right, which is actually quarried and cut into kind of rough rectangular forms, okay? Large slabs can be called cut stone. Small blocks tend to be called ashlar, right? So I'm going to show you a bunch of examples of quarries, some of which are old photographs, some of which are newer photographs, right? The basic technology really hasn't changed that much, right? It's still kind of a primitive way of getting your materials, right? But it's looking something like this. So if we're looking at this particular photograph, right, we could see that we have some, relatively rough square faces that they've been working with to cut off individual chunks. Then we have a bunch of these pieces of rubble, right, that might have one good side, and so we don't want to waste those. So if we can, we'll use those as part of the building, and we'll try to sell those too, right? We also have something that's called flagstone, right? It's a very thin slab of stone, and certain materials work better as flagstone than other materials, right? So, for example, you're very unlikely to find a granite flagstone, right? You're very likely to find a slate-based or a quartzite-based or something like that form of flagstone, right? So it varies a little bit, but it can be cut rectangular, right? Or it can be cut or left as an irregular outline, depending on the kind of the look that you're going for, right? It's used primarily for flooring or for paving. Okay? So if we move on to quarrying limestone, right? And so this process would be similar for granite, right? Similar for a lot of the stones. In this particular case, I believe the book walks through limestone specifically, so we're going to walk through limestone, but it translates roughly to the other examples, right? So we have what's called a diamond belt saw, right, that divides the bedrock into long cuts. So we're thinking somewhere in the neighborhood of 50 feet, right, by about 12 feet high. So this is a really big chunk of stone that we're trying to cut, right? And so here's our example here, right? We have our powered saw here, right? It moves along a set of tracks, and it's cutting 12 feet deep this big chunk, this big block, right? It's just making a cut, okay? After that, right, we have a person who's operating a horizontal drill, right? Could be a machine that comes in and drills a series of holes that are all at the same level, right, through the bottom until they get to this saw cut, right? So we're drilling along the bottom. The reason we can't just take a saw, right, and cut along the bottom is the weight of the stone would compress on top of the saw, and we'd never actually be able to turn the saw, right? If we drill it instead, right, we can remove the material, and there's still enough support so that the wall isn't collapsing down, or the stone isn't collapsing down on our material, right? Same thing happens if you're ever on a table saw and you try to cut wood. You have to be careful of how you cut it because it can pinch, right? So anyway, we drill those points. So here's an example of a limestone saw. This was the example that I was picking, right? But there's another example in the book that works more like a chainsaw. There are obviously a variety of saws out there. This one is limited, right, in its how deep it can cut by the size of the blade, right? So these kinds of things vary. Notice that it is on tracks, right? It probably uses water as a lubricant, right, to help you actually cut through the material. If you've ever done any stonework, right, and tried to cut through material, if you have the right equipment, it's not that hard to cut, right? So, for example, if you've ever cut granite or fabricated granite counters, really it's not that bad, right? As long as you have the right diamond wheels and that sort of thing to be able to cut it and grind it the way you want. Okay? So if we look from a little bit further away at a limestone quarry, right? Part of the problem with a quarry is it's inherently messy, right? This is not a clean operation. It's not inside a building, right? We have a mountainside, right, or a mountaintop that's made of limestone, right? We go out to that particular piece and we try to cut it into pieces that we can use, right? And each time we cut and remove a particular piece, right, it leaves us with a shelf and some kind of an awkward position with where are we going to get our next piece from, right? And so if you look at something like this, you notice that there's all kinds of makeshift little roads that get us down to wherever it is that we're cutting our blocks from, right? And so depending on how this process is going along, we may find that, you know what, we want to come back and start working over here, right? We may find that we end up with a stranded truck because some stuff fell around it, right? Those kinds of things happen, right? And when you look at a photo like this, it's kind of fun because you can pick on that sort of thing, right? So after we make that long cut, right, and after we drill all the holes underneath, right, we stick down that little crack of the cut, right, and this varies a little bit depending on what technology you have. The example in the books example is they put these air pillows in, right. Once they put the pillows in along that cut, they inflate the pillows with air, right, and that expansion causes the solid rock to crack right along where all those drill points are at the bottom, right? When that happens and it cracks, this big piece of limestone or granite or whatever type of stone it is, right, falls over, right, and then they can start to work with that big chunk of rock, right, or that big chunk of stone, okay? Other options for this, if you didn't have the air pillows, right, you could simply drill holes, right, or use that saw cut, fill it with water, wait for it to freeze, right, if you have the ability to do that, and that would crack the stone, right? Sometimes if you're trying to do a foundation, right, and you run across a big boulder that's underneath, like let's say you're up in Tahoe, right, and you need to pour a foundation, you have a giant rock that's in the way, very common in Tahoe, right? You have to get rid of a piece of the rock. How are you going to do it, right? If it's of the right time of year, right, you drill the holes, fill them with water, wait for it to freeze overnight, and suddenly you have a nice cracked piece that you can then remove, right? Other options would be to fill that hole with an epoxy, right? The chemical reaction causes the epoxy to expand. Suddenly you've cracked it, broken it, and been able to remove it, right? So there's a whole bunch of different options. The air seems to be the simplest on a reusable basis, right? You have the pillows. It's pretty easy. You're in a quarry. You move those pillows in the right place, inflate them, it cracks the wall, right? You don't have to wait for it to freeze or something like that, okay? So this is called turning the cut, right, which is breaking the block free of the solid background. These little, I think this drawing is a little bit confusing, right? We have all these little lines that are going along here. It makes it look like this is all cracked. It's actually the air hoses that go to the pillows, right? So it's a bit confusing. So we're getting to that. So we work our way down from the bigger pieces smaller, right? So here we are breaking our blocks. We're looking at the top, right? So they started with this first set of limestone to a flat base here, right? After we've cut down that far, we're going to start the next round and get a little bit further, right? So they keep working their way down to break it into the blocks, right? After we have that, right, the turning of the main block, right, then we're going to break that main block into smaller pieces that are more manageable. Yeah. It could be. I mean, you would not want to waste, if let's say you had a nice solid piece of limestone, you wouldn't really want to waste that nice solid piece by grinding it into a fine powder. What you would do is at the quarry, you would make as many of these bigger blocks as you could, and you take all the extra rubble and stuff and you grind that up to use, right? So you wouldn't just like, oh, let's just start digging. You try to use it for its maximum purpose, right? For like cement, it's going to vary based on wherever you are. Do you have access to a quarry like this that might have leftover spoils? Or, do you have access to a beach where there's a bunch of seashells and you can collect those? Not, individually, but in a more mechanical fashion, right? They don't have a group of people that comb the beach every morning and collect seashells to make concrete. Not quite, right? But depending on what you have access to, that's what you'd get it from. So if you have access to a quarry that has limestone, yeah, you'd get it from there, right? So we're going to break this down. Usually they're using just something as mechanical as a wedge, right, and a sledgehammer to crack and break these blocks, right? So they drill the hole. Here's an example, right? They've drilled the hole down through. Likewise, they've drilled the hole down through, right? So this gives you some idea of the size of these blocks. They're still pretty big, right? And then they put these wedges in at strategic points. And the better you are as a quarry worker, the more you intuitively know where it's going to split and where you should drill these holes, right? And so in this particular example, they're getting this ready to split, right? Once they drive these little wedges in, it will crack along those joints and will have pieces that are yet smaller that they can then begin to work with, right? And so they continue to break them down until they become a manageable size, right? And so that manageable size varies, okay? How many people have ever been to a granite shop where they're selling granite sheets, right? So if you've been into one of those places, right, especially where you see the rough cut sheets, right, and you look at that nice polished surface, usually the border is a jagged piece, and usually somewhere in there's these little holes that are left over from where they split it out, right? So in the case of a granite counter, say, right, they would break it into a manageable block size, right, which is usually about the size of one of those pieces that you would buy in the store, right? They then take that block mechanically to a saw, right, relatively close on site. It's not a big transportation process, right? Usually it's a wet bandsaw or something, and that wet bandsaw in granite, right, would slice those thin pieces, right? It's still a very rough cut. It's not polished by any means, right? After they slice those rough cuts, they take those slabs, right, which is what they call them now, flatten them out, right, and then grind the surface and polish the surface to give you what your countertop would be, right? For something like limestone, it's less likely that we're going to go straight to cutting it into slabs. More likely, we're going to try to use it as blocks, right, and put those blocks together as part of a building. Though, right, we passed around plenty of these little travertine type examples, which is basically taking limestone and slicing it up into little pieces, right? Now, if you're making 12-inch by 12-inch tiles, right, you can use relatively smaller blocks, right, and cut those blocks up. So you keep working your way down into the minimum size, right? A granite counter is going to be a much bigger slab than something that's going to make little tiles, right? So part of the problem with quarrying is it's a messy process, right? There's a lot of offfall. There's a lot of spoils to it. This is a great use, right? If we're looking at something like this that's a limestone quarry, there's a lot of extra stuff that could really easily be ground up and used in cement, right? And that's stuff that the quarry is happy to get rid of because they have to put it somewhere while they continue to manufacture more and more of the limestone. And it's not really manufacture, while they continue to, extract more and more limestone from the land, right? So if you're a stone producer, right, you're going to work from the architect's drawings to produce shop drawings of the pieces that are actually needed, right? And there's a couple different types, and we'll talk about them in just a second. The shop drawings, and this is primarily for ashlar, right, are going to show the dimensions of each individual stone that's to be shaped, right? And by shaped, it may mean, cutting it into a rough size. It may mean getting it into a rough size and then splitting the face surface so that it has a rough texture to it without, these kinds of lines in it. That might be undesirable, right? So they're going to get it to the rough shape and size that it needs to be, right? The architect is then going to review the shop drawings and approve them and say, yes, these are the correct sizes. I do want it, and this is what it's going to look like, right? The rough blocks of stone are then refined into smaller pieces, right? They're basically made, right? The stone can be plain flat. It can be cut into smaller pieces. It could be turned on a lathe if you were, say, doing a column, right? So it's going to be basically manufactured into whatever the ultimate shape needs to be. If you're making a granite slab for a countertop, you're going to polish it and make it into a granite slab, right? The stones are then labeled and delivered to the building site, right? Hopefully in the order that they need to be used, right? So, stone is used in two different ways in buildings, right? It can be laid in mortar like bricks for stone masonry, right? Or it can be attached to structural walls as cladding, right? So this is a lot like brick, right? We can have a purely structural building that's all out of stone, right? Or we can have a building that has a structural surface that's, say, concrete or some other internal structure, and we're just applying it to the outside surface for the look of a stone building, right? And so that's going to vary, right? In terms of stone classifications, right, we have rubble, which is the rough, irregular stone, right? It tends to give more of a rustic feel, right? It can be a little bit more shaped. If it's more shaped, it's going to be a squared stone, right? It's made approximately square or rectangular. I say square in kind of a loose term, right? But it's still left relatively rough. The thing about the top two, either rubble or squared stone, right, is that they're not specified by the architect in terms of where they go in the building, right? It's left up to the mason to decide. If we move into something that's called ashlar, right, each stone is cut to a very precise dimension, and it belongs in a very specific place in the overall wall, right? So it's designed by the architect and needs to be made exactly like that, okay? So if we talk about seeing stone, say, on a blueprint, right, we need a way of kind of representing it, right? If we're doing either rubble or squared stone, right, which are the first two types, they will be drawn in kind of in a general arrangement. This is kind of what I want it to look like by the architect, okay? But it's not something that's very specific, right? Just kind of this is generally what I want it to look like, right? So there aren't details that specify this size, that size, okay? If we're looking at ashlar, right, it's designed exactly by the architect. Each of those stones is specific. It needs to look like this. This is how I want it made. Okay? So it's up to the architect to decide, not the mason to decide where it goes. Right? In this particular instance, right, the architect shows the precise location on the plans. The fabricator makes shop drawings that say these are the size pieces we're going to make, right, and this is where they go. The architect then reviews and says, yes, I like this. Go ahead and make them. Okay? So this kind of helps show these a little bit. We have our random rubble, right, or our uncoursed, roughly squared stone, right? Both of these are up to the mason, right, who's actually making the building or making the veneer, right, to decide this rock looks like it goes here, right? And there's certainly an art to this. If you've seen, natural stone fireplaces or things like that, if you have a really good mason who's doing it, the fireplaces turn out absolutely beautiful, but the mason is looking, I have these stones. These are the ones that I'm going to build with. How do they go on the wall? Where do I place them, and how do they look, right? So it's an artistic thing, and a lot of stonemasons are kind of artists, in a sense, in terms of what they do and their style and how they put it together. So these top two, right, are up to the mason to decide where the stones go, right? When we get down to these bottom three, right, and I probably should move that one down a little bit so it stays in this category, we have our ashlar, right? And we have coursed ashlar, right? Even though the courses vary in thickness, right, they still fall in courses. We have coursed ashlar, but we have a broken bond, so we have smaller pieces that make up a course, right? And then we have a random ashlar, right, where there isn't a course and the pieces fit together, right? Again, all of those designed by the architect, each piece individually made for a specific location on the building, right? So rubble stonework is laid much like brickwork, right? It requires the mason's skills to select each stone carefully and decide where it belongs, right? And so depending on the skill of the mason, the wall is going to turn out better or worse, right? Ashlar stonework, scripted in terms of where it goes, larger pieces, and again, this is part of the ashlar look of a building, might be too big for a person to lift easily, so you might have to have some special equipment on site to help you lift these stones into place because they're manufactured, they're made bigger, right? So that can end up costing a little bit more, okay? So as you put these stones together, and this is the same whether it's the random rubble or whether it's the ashlar, The initial joints, right, once you put one on top of the other, right? So let's say we're in ashlar because it's a little bit simpler, right? And I don't have, I have the small samples that I passed around, but I don't have any big ashlar examples that I can show you, right? So we're going to use bricks and pretend these are natural stone, right? The concept is still the same, right? So when I put these two pieces together, right, there's a bed joint of mortar, right, that ties the two together. What I'm going to do after I put those two together, right, is I'm going to go through and I'm going to rake or excavate out the front bit of this mortar, right? So I'm going to cut out that front bit of mortar a ½ inch to a full inch, right, depending on the sizes of the stones. So there's still mortar that's causing it to bear correctly, right? But I'm deliberately pulling out and scraping out the front part of that mortar, okay? So that gets the mortar out, right? And it prevents uneven settling of the stones or any kind of weird stuff that might happen to the edges of the stones, right? After the mortar has fully cured, right, so the structure is intact, right, then I'll go back and point the wall. And by pointing, basically that means I'm going to make a really flexible, right, workable mortar, right, and I'm going to fill in all those gaps that I created when I raked the joints, okay? So that ½ inch thick gap, I'm going to go and I'm going to fill in with a nice flexible mortar, and the purpose of this mortar is to basically provide the weather seal, right, so that it's very flexible. It goes around all of the individual little irregularities in the stone and make sure we have a nice weatherproof seal on that outside grout, basically. It's a lot like grouting tile, really. Does that make sense? Yeah? Okay. It's a low-strength, high workability mortar to go in and around every one of those little grooves and imperfections. Okay? So once we have the stone in its place, right, a lot of times we'll want to keep the moisture out, right? We'll want to keep the weather out. We can apply, right, some kind of a stone sealer on the surface to keep that moisture out and prevent it from causing issues, right? Anybody been to the Century Theater in Walnut Creek? Right? A few people. Did you ever look down on the ground outside? Maybe, if you were walking, right? It's made up of a bunch of brick pavers, right? So it's not natural stone, right? But it's a really good example of stone sealer, right? That particular area, for whatever reason, they chose to coat with a sealer that has a gloss seal to it, right? So if you walk around, all of those pavers are shiny, right? And so you can tell that it has the sealer on it because the pavers have been made shiny. By their nature, they're not shiny, right? And so that's an easy way of seeing that seal, right? And for whatever reason they decided to seal it, probably has to do with underwater conditions and not letting the water go through those pavers into the subsoil or whatever, which is a whole side note because a lot of times engineers actually want you to let the water go in so you're not collecting the water and then putting it somewhere else. So there's big challenges related to that particular thing, right? The other thing that can happen, though, if you seal the stone, is it can make it slipperier when it's wet, right? So you have to be aware of which sealer you're using and what it does, right? Not all sealers are shiny, so certainly you could seal a particular set of stone without doing that, right? So let's look at an actual example. This is a rough stone that's uncoursed, right, which means that it was designed by whoever, the mason who was actually laying the stone in this particular example. This is up in the Swiss Alps, right? Very simple in its design of a building, right? Very stone-like from the outside. But this is a pretty good example of using, right, natural native stone and building your building, right? My guess is, and I've never actually seen the construction drawings for this particular building, my guess is that this is a veneer. It's not an actual structural stone building, but it's in the same vein, right? This is what it looks like from the inside, right? And so to me, this is kind of a fun example of seeing the extremes where you can have something from the outside that looks and has that kind of rustic feel to it, yet you can come inside and it can be one of the most clean, unbelievably modern buildings you've ever seen, right? And so it happens to have an unbelievable view, too, which doesn't hurt. So we've got a couple more pictures of outside, right? You can tell it's perched right on the side of this mountain, right? There's the door. You have a taste of the modern interior there, right? So just an example, okay? So we move into the concrete masonry unit, which is kind of attached to the stone chapter for some unknown reason. But basically, it is a concrete unit that is sold as a unit, right? So instead of having a poured in place or a precast concrete piece, right, we're making it into a smaller piece that's a lot like a brick, right? The hollow units are almost always slang termed as concrete blocks, right? If you're on the older side, you may have heard the term cinder block before, right? That had to do with the manufacturing process, right, and the byproducts that used to be in them. They are now no longer cinder blocks, right? They are concrete blocks. There are larger solid units. There is actually one behind you over here in the corner that is way too heavy to lug around, right? That would be used for a retaining wall purpose. It has a split face, so it looks more like a natural stone, even though it's actually manufactured. But you guys can come over and look at that at some point, but I didn't feel like making you all carry it around, right? So it's a little bit larger unit. It's not as common to see the larger units, but certainly they exist, right? So in terms of the manufacturing process, right, we don't have to go through the firing process that we do in brick because it's concrete, right, and it's going to cure on its own. So what do? We need a very stiff concrete mix, right, because we don't want too much water. We want it to be high strength, right? And so we're going to vibrate that stiff mix into a metal mold, right? Once we have that concrete in the metal mold, right, I don't have a mold here, so I can't show you, right? They take the mold, they flip it over, right? They pull the mold off, and we have the concrete block left over, okay? Part of the reason we need a really stiff concrete mix, right, is we don't want it to slump, right? So this is a no-slump concrete that's making these bricks, right? I have a variety of these bricks that I'm going to start passing around in a second. These are obviously much heavier than the bricks to pass around, right? These molds tend to be reused, right after you make one, you start the next one, right? They can produce, one mold can produce 1,000 or more units per hour, right? So it's a very quick process, right, to produce these. The wet blocks are then steam cured in racks, right? So we're accelerating the curing process just like we would do, right, in prefabricated concrete, right, or offsite fabricated concrete. The units are then bundled onto wooden pallets and shipped to the construction site, shipped to Home Depot, shipped to wherever you're going to buy them from. Okay? They can be made in a variety of shapes and sizes. Generally, they're based on an 8-inch cubic module, right? Loosely, right? So if we're looking at something like this particular one, for example, right, or this particular one, for example, which are slightly different, right? They're both roughly the same size. Notice they're basically the same height. So this is very different from brick, right? Likewise, if I were to put these two together, right, even though they're different and they have some different qualities, they're basically the same size, okay? And so that's one of the important things to realize about a concrete block versus brick, right? It has a nominal size of 8 by 8 by 16, okay? But it's not the actual size of the brick. And so what they do is they take each of these measurements and they subtract how much grout or how much mortar would be in between the bricks, right? And that gets us the actual size of the brick. So the actual size would be 7 5/8 by 7 5/8 by 15 5/8, which is telling you that the mortar is 3/8 of an inch thick, right? So that's what they're anticipating using, right? Guess what? It says it down here, right? You guys are all so smart, right? So what does this mean for designing the building, right? Well, if I'm using something that's based on this 8 by 8 by 16 module, right, my building better be based on the 8 by 8 by 16 module, right? So if you as the designer or the architect know that you're going to be building in a concrete masonry unit, right, you can't have an odd-sized room. It doesn't work, right? Because each of these corners has to fall within a certain number of blocks, right? So 16, 16, 16, 8, right? It's all going to add up. It has to, right? Likewise, when we turn the corner, you can't have a half a block or 2/3 of a block, right? It doesn't work. So could you cut one of these blocks? Sure, right? But it kind of defeats the purpose of being able to use these nice prefabricated pieces that come to the site as a standard size, right? So you need to be very careful when you're designing a building, okay? So how do we go about laying these in the first place? It's a lot like bricks. Okay? So we place a bed of mortar on the footing, right? I know this is a little blown out picture, but you can look in the book or you can look online and it's a little bit better, right? So we have our footing, right, that's been poured, right? The footing, the purpose of the footing is to, you guys remember a couple, right? Transfer all the load down into the soil, right? So we're spreading out the weight that's coming down, right, into an allowable stress that the soil can support. Okay, so we have that footing. We spread our bed of mortar on top of the footing, right, to tie these blocks to that, right? We start with our first course of blocks for a lead, just like we would on a brick building, right? Basically, we're doing the corner first, right? Mortar's applied at the head joint, right, to be applied at each end of the block, right? It just means that you put the first block down, right? Then you take the next piece, you have a bed joint that's on the footing, right? But on the block itself, you put the mortar on the head joint so that when you glue it together, right? So let me try to illustrate this here a little bit better, right? So I have here's my footing, right? I put my mortar down on my footing. I take this block, right, and I put it down. I'm ready to attach the next block, right, in series. I already have, this one's much heavier. I already have the mortar on the ground, right, but I apply the mortar on the head of this block so that when I put it into place, right, the mortar's already on this surface and can start to tie these two pieces together. Okay? I continue to work up, right, the lead at the corner, right, of the wall in that kind of diagonal pattern, right? As each course is started, right, I might use a story pole. I could use a tape measure because I want to make sure that my joints are consistent and that they're falling at their right interval. The nice thing about using something like a story pole like this, you guys all see this little piece that has the marks on it, right, is that that's something I can reuse over and over in the building, right? So I can work on it on one corner, make sure everything lines up. I can move to the next corner, make sure everything lines up. And it's a really quick process, assuming that my footing is level the way it should be. Right? It's a really quick process to do it with this. This is the kind of thing that dates back to a building tradition in Japan, right, where they would create a story pole before they started building, and the whole building would be based off this one story pole, every measurement in the building. That's what the purpose of the story pole was, right? So you didn't have a tape measure, you had a story pole. Right? So same thing happens here, and we work our way up. Okay? We're continuing up with our lead here, right? So each course as we go up is, of course, checked for level and also for plumb, right? So level is up top, plumb is going up vertically, right? Likewise, we want to make sure that none of the blocks are kind of out, right? Sticking out, leaning in, that sort of thing. It's a little bit easier with concrete blocks than it would be with brick because bricks have much smaller pieces, right? Concrete blocks are bigger. It's easier to make sure that they're in line, okay? So we check for level, we check for plumb, right? So afterward, the joints, right, are tooled, right, with a concave profile, so they stick in slightly, right, each. And then a soft brush will remove any of the extra little crumbs, right, that are on the surface that we don't want, right? After we have our two leads on either side, we stretch a line across, and just like with brick, we lay our mortar down, and we put our blocks in, right, in between each of the leads. And it's a really quick and simple process, right? Again, right, the mortar is always on the bed first. We put the head mortar, right, on the brick to be put in. Okay? As we get to the last block, right, the last block in a particular course is called a closer, right, because it closes off that particular piece, right? This one's always a little bit tricky to get in, so we end up, and they tend to refer to this as buttering, right? When they put the mortar on these pieces ahead of time, it's like buttering bread, right? But they're buttering the concrete block, okay? So what they do, right, is they put the mortar, right, inside this hole for the closer, and they also put it on the outside of this block to be dropped in, right? And that's to make sure that we're being redundant, right? Even though we end up with a little bit of extra mortar, we want to make sure that it has plenty to tie the whole wall together, right? It's easy when we're on our regular course to put some mortar on the head right, and then push it up against it, we know that we have good mortar contact, right? When it's that closer and we're dropping it in between two other pieces, we have to make sure that there's enough of that mortar in between the two to seal that wall together, right? So this is just a redundant way of making sure that we get there, right? So just like with brick, we run the risk in this kind of building construction, right, in earthquake zones of having a lot of individual pieces that are being tied together. So if we have a weird lateral force, like an earthquake, that's acting through a building, that's rippling through a building, it's going to have a tendency to want to break all the individual joints across. So we can do some stuff that helps tie it together, which is why, even in the state of California, we see a lot of construction in concrete blocks, right? A lot of those walls on the sides of freeways, those are like the most common, right? They're in the state of California. They're subject to lateral loads, but we can get away with it because we can do certain things that help to reinforce these blocks, okay? So number one, we can put reinforcing in between, right, in the mortar between two courses of bricks, right, which can help tie those together, tie it as a longer piece, right? So you can see it here. This one's in the shape of a truss. They might be in the shape of like a ladder, right, where they have rungs that go across. Yeah. Vertical rebar. So this is probably not the best example of a seismic reinforcing, but the concept is still there. So the point is that in a concrete masonry wall, we have a bunch of internal voids, right? And so depending on how we design our rebar, right, we can run rebar up and around inside one of these walls, right, which gives us some extra reinforcing. Now the problem is if we have rebar, we have to fill the cavity wherever the rebar is for it to serve any purpose, right? So we end up pouring concrete in. The advantage there, though, is we don't have to build formwork because the formwork already exists, right? So it's a good kind of economical way, which is part of why we see a lot of freeways that have this kind of work. It takes less, right? So here we've got our concrete blocks here. Notice that we've got a channel for rebar running through this, right? Likewise, this particular block is a good example of that, right? We have a hole here that allows us to run reinforcing through it, right? So if I flip this over and run it that way, I could put reinforcing in here, right, which would help tie the wall together. Likewise, these dowels are coming up from underneath, right, tied into the footing, right? So this is a much better example of how we would do it here in the state of California, subject to earthquake loads, okay? After we have this reinforcing in and we've built our wall up, right, we can fill the wall with concrete, right, and it's becoming kind of a hybrid of a concrete masonry unit wall and an actual concrete wall, right? And our reinforcing and stuff can help support larger structural loads, right? So it's a pretty good economical way of building a wall that isn't entirely concrete but has a lot of the strength of a concrete wall, right? So it's kind of that internal hybrid strategy. Okay, so we're done with concrete masonry units. We're done with stone, right? We're done with brick. So next class we have our midterm and we test our beams, right? Then the following week when we get back after that, right, we move on to steel. So we've kind of covered the concrete, brick, stone realm. Make sense? Any other questions before you go? So chapters being covered are 1, 2, 8, 9, 13, 14, and 15.